So questions? Any questions? We've covered, so far we've talked about Gauss's law, we've done the general electric field equations for line charges, surface charges, point charges. We've talked about, we basically are going through electrostatics. Any questions about, okay, so what happens after Gauss's law? We get voltage. Y'all remember voltage? Some of the books, if you look, voltage is probably your best friend because it makes, it's a scalar potential. Is anybody got any questions about the divergence forms of Gauss's law? Y'all know what it is, right? How many do? It's worrisome. Whenever I see these blank stares, I'm like, what? I'll do that, then I'll do voltage. The divergence form of Gauss's law is divergence of V is the charge density rho V. I want to be clear about this. You have to know this. It's trivial, you have to know it. Now, because D is equal to epsilon E, this becomes simply divergence of E is equal to rho V over epsilon. Do y'all follow me, class? Both of these are important. What it really says is if you take the divergence of D and it's zero, there's no charge in the region, no free charge. And I have to be clear about one thing. Please give me your attention on this. So people get really mixed up in this. You've had microelectronics and solid state physics. Do y'all agree? You've had, right? How many have? How many have had microelectronics with Dr. New or somebody like that? You're taking it now? Well, he must have gone over this. When you have silicon, it has a lattice, it's crystalline silicon, where there's bound positive charge, right? That center charge can't move, but there are free electrons that can move. Do y'all follow me? Now, the total charge density over any volume is zero. There's the same amount of electrons as there are, quote, holes, really positive ions, right? However, the free electrons can move. Now, if there is no external charge perturbation, divergence of D in silicon will be zero. Do y'all follow me? Even though there's free charge in terms of there's free electrons and there's bound holes or bound protons. Do y'all follow me, class? All right, it's important to realize this. However, if I take a chunk of charge and I place it in a region, then the divergence of D will not be zero. This is very important to follow. And this is the differential form, or the point form of Gauss's law. The integral form is the integral of d dot ds over the closed surface is equal to the charge enclosed in the surface. That's these the two, they're one and the same. You can prove either one from the other. All right, now, just so you know, in the back of your book, you'll be asked to do this. Just telling you that I'll ask this from you on a quiz or a test. In the back of the book, back cover, you're going to see something under the vector operations that says divergence. Do y'all have books here? If you don't, look at your friends or just look online. You're going to see three forms of divergence equations: the Cartesian, cylindrical, and spherical. Do y'all see that? Now the one thing to, everybody, how many see this, right? Yeah. If you don't have a book, you don't have a book. Okay, you got it, everybody? Far back, you guys see it? I know you got other things to do. Video games are very important. You okay with this? It's worthless. Anyway, I'm trying to help you here. Now, listen to me. If you take a divergence of a constant, it is zero. Don't try to make it be non-zero. Do y'all follow me? Hear me on this, class? I want to do at least one of these. Let's do one in Cartesian coordinates, make cylindrical. Just because people have a way of saying, oh, I got this. And they don't. They come to a quiz, and I promise you, no matter what I say, they will fall on their face because they're overconfident. They really haven't done problems with it. They just think I got it. So I'm going to give you one. Suppose D itself, this would be like a quiz problem. This is going to be a more simplified version because it's going to be in Cartesian. Usually I give it cylindrical or spherical. But suppose I give you D is 2xy ax plus 4z y ay plus 10x squared az. And this would be in terms of coulombs per meter squared. That would be the D field. Got me? Just look at the back of the book and work with me. Now, if I ask you the charge density at a point, I'm not going to define the point yet. Following? So the question would be, how do you find the charge density at like x equals 1, y equals 2, z equals 0? Follow me on this, class? That would be the question. Well, according to this, I have to do the divergence of D. It is in Cartesian coordinates. So what is divergence of D in Cartesian coordinates? Just look at it. Make sure you see this. It's a scalar, not a vector. It's the derivative with respect to x of D of x. This is D of x, so it would be 2xy plus the derivative with respect to y of D of y. This would be D of y plus the derivative with respect to z of D of z. This would be D of z. Everybody follow me? I've just taken the mathematical form and placed in there the information or the coefficient variables, the unit vectors that I want you to do the operations on. Do y'all follow me on this class? Can you all see this? All right, so do it with me. And there are tons of people who make mistakes on it. So what is the derivative of this with respect to x? 2y. Plus, what's the derivative of that with respect to y? 4z. What's the derivative of that with respect to z? Everybody hear that? 0. I promise you I'll see people say it can't be 0. It's 10x squared. It has to be. I mean, I'm just telling you what I've seen, and I'm warning you, trying to really underscore the warning. I know you're not stupid, but sometimes you're nervous, and you just do things because it's impulsive. You're trying to get points. That's a really silly way to go about business. Do y'all follow me in this class? So that would be the value. Now, here's a question. This is rho v, right? What is rho v for, say, x equals 1, y equals 0, and z equals 1? Just look at it. Is there any x in that equation? So who cares what x is? It could be a billion. Do y'all follow me? Next, y is 0. It gets rid of this, right? Finally, z is 1. Therefore, it is 4. Now, it really is that simple. But if you look at the cylindrical and spherical forms, just take a look for a second. Now they've got derivatives where you have to multiply rho or r squared times something. Do you all see that? Oftentimes, people get confused with that. I'm going to encourage you to make sure you do these homework problems that I give you that have to do with divergence, just so you exposed yourself to them. You don't panic on a quiz. Do y'all hear me? Now, oftentimes, yes, sir.
For the points you did 0, 1, 1, that the answer would be 6.
For y1, z1, if y is 1, this is going to be 2. Z is 1, this is going to be 4, so it would be 6. But you can extrapolate to any values. What's the only place where the charge is 0? Come on. It doesn't matter with x, right? X can be anything, but it has to be yz is 0. Do y'all follow me? And if I asked you, if I said if z is 5, where would y be so the charge is 0? Do y'all follow me? In other words, I could ask you to back out a value if the charge is 0. That's the constraining factor, and you'd have to calculate the other factor. Y'all follow me, class? So it's basically something where if you understand this, it will not be hard. But I know it's so easy to fall prey for the fact I got this, and then the form of the question confuses you. Instead of asking for the divergence of D, I ask for rho V, and I ask for where the charge density is 0, if like X is 3, Y is 5. In other words, what value is C? Do y'all follow? People get confused in that if they haven't done it. All right, enough about that. Now, any other questions? Because I'm going to go to voltage next. Now, voltage is your best friend at calculating things because it's a scalar, unlike the vector quantities we've been dealing with. But calculating the voltage will allow us to calculate all the vector quantities, which is super nice. So, here's how we go about explaining the development of the term voltage. We start with saying, I have an electric field that's caused by something. It's everywhere in free space. All right? We just have this field. It's available to us. Now, we place a charge in here. And the charge has a value Q. If I put a charge in an electric field, I have a force. Do you all agree? The force on this charge, and I'll call it F from the actual electric field, and I'll just call it F of F. This here is just Q times E. It's a vector. Do you all agree with that? Right? All right. Now, if this thing's allowed to move, the field moves it. Let's say it moves it from point A to point B. All right. So in other words, this is going to be the path that the actual force is allowed to move on. Y'all follow? So the external field would do work. Do y'all agree with this? The fundamental thing is if you have a force and you integrate the force over the distance the force is applied over, like to an object, you get the work. So the work that the field does would be equal to the integral from A to B of the E field, which is, of the force, which is Q, times E, right here, dot dl. Because Q is a scalar value. Do you all agree with that? Now that's the work that the field would do. If I'm here, and I say whatever the work the field does, if an external force would push it in the opposite direction, just work with me for a second. If I was here, the force from the field is this way, and I pushed it this way, then I would do positive work, right? But the field would do negative work. Do y'all follow me? This is positive work right here, because I move from this point to this point in the direction of the force. Do y'all follow me? How many do, right? It's important to get a concept. Just realize this. If the force is allowed to move the object, and it moves the object, then it does positive. However, if I'm here, and say the charge is here, and I push it this way, then I do the external force do positive work, but the field does, quote, negative work. You got a handle on that, class? All right, so I can say that the work an external force does, and these terms are, you can choose your own symbols for these, but this is for an external force, would be minus Q times the integral from A to B of E dot dl. Everybody with me on that? Good with that? That should make sense. You can obviously see the sum total of the external forces work and the work the field does is 0. That's just an obvious fact, right? Over any distance. Well, what we do is take a look at this. This is an external force right here. It's me. If you divide that by the charge, now we get something called the voltage. And it's actually the voltage measured from point B to A. And I'm going to get to that in a second. This is the voltage. Voltage always has to do with, I call it an electrical pressure. That's the term I use. And it's really like an atmospheric pressure, or a pressure in a pipe, and the higher the pressure is at one end compared to another end, the more force there is in moving an object, a charge for instance, from the point of high pressure to the point of low pressure, the high voltage to low voltage. Charge will always move from a high voltage to a low voltage if allowed to. Do you all follow me in this class? And this is things you've learned in circuits, right? So if you look at this, what it means is, and this is the way he has it in the book, if you have these 2 points, I'll do it this way. He's going to have VBA is equal to VB minus VA, and it's equal to minus the integral from A to B of B dot DL. And can you see this formula in the book? Anybody? I don't know what page it's on, but you see it what page?
160.
What formula number is it? What's the number of the formula?
3.69.
Thank you. Somewhere in there. You guys got the idea. All right, so that's the definition of voltage, and it's real important you get a handle on one thing. When you talk about voltage, and let me erase this, I want to give you a good idea. You've already had voltage, but you look at this, it's real important. We've got VBA, right? 2 points. Voltage is always between 2 points. It's never just 10,000 volts. That would be an assumed zero potential at ground. 10,000 volts by itself doesn't mean a darn thing unless you know where the ground is, which in most standard industrial applications, residential applications, it's the earth. That's where the earth ground is, where zero potential is. So do this. This is your positive lead of your meter. This is the negative lead of your meter. Now it's important to appreciate that. So if I take a look and I get VBA, and it's positive, it says at point B, if I stuck a positive probe there, and then I took the negative or ground lead on the meter and put it here, this will be the voltage I will measure. All right? You all hear me on this? It may seem trivial, but it's not. I see people make mistakes on this because they don't have a good appreciation for this. So I'm going to do the classic problem first of all. There's a lot of them. So let's say we have a point charge. I'm going to show you the real beauty about this in a second. Suppose I have a point charge Q, right? Now, I know the electric field at any given distance r from this, the electric field is just going to be equal to Q over 4 pi epsilon naught r squared in the AR direction. I don't think there's any argument about that. You all agree? All right, let's find the voltage between 2 points. So here, I'm going to call this point right here B, is going to be right here, and then I'm going to have a point A out here. I'm going to execute that formula, hopefully. And remember, this is where my positive lead will be. This is where my negative lead will be. And I'm trying to say B is really the radius right here. And this is the radius here. And therefore, A is much greater than B. I'm just trying to give you an example. You all follow me? Now, I know you've had this in physics, but based on my experience, there's a lot of people who don't really have this down pat. So when I'm going to calculate the voltage between B and A, I'm going to use this formula, and I'll do it right here. So I'm going to say VB minus VA is equal to minus the integral from A to B, so it's from here, A to B of the electric field, which is Q over 4 pi epsilon naught r squared, AR, right? Dot DL. And we could, this would be spherical coordinates, and just listen to me now. Technically, the differential length in spherical coordinates would be equal to dr AR plus, and then you're going to have an r d theta a theta, and then there's going to be an r sine theta, and it would be d phi a phi. I'm just putting this down. I've given you these differential links. Do you remember that? I sent you a bunch of stuff with the different coordinate system and differential links and differential surfaces. How many remember that? It's on OneNote if you haven't seen it. Now the differential links, you can't read this, sorry. Yeah, it's on, this is dr plus r d theta d theta right here. And that's going to be r sine theta d phi a phi. Now, the only reason I did this is to say when you do the dot product of dl, technically it would be dl, right? Let me just put it in talk about this. Remember I said ar is 1, ar anything else like a theta and a phi is 0. Do y'all remember that? You'll notice the only component you care about is this component. The dot product will get rid of that. Do y'all see that, class? How many do? So I'm not even going to bother writing. In his book, he doesn't even really go through that. He's going to say what this really is just AR dr. Simply because the other two will dot out to 0. So he doesn't keep writing it, but you should be aware of it. Now when you do this, I get AR dot AR, which is 1. So that becomes 1. And then I integrate that dr, right? Maybe I did like a capital R here, but I put a small one. All right. If you integrate that, what do you get? Well, I'm going to take the constant out. I have minus q 4 pi epsilon naught. And then I integrate 1 over r squared, which is minus 1 over r. Is it not, class? Y'all agree with that? So that minus sign, I get rid of this, and I have simply and I'm going to have, well, I'll do it this way. Minus, then I have minus 1 over r, evaluated a to b. And that will be q over 4 pi epsilon naught. And then you're going to have and here's what happens here. He'll have this in his book, I think. This is positive, that's negative, right? Y'all follow me in this class? In his book, I want to find this in the book, by the way. He has something. And trying to get this. This is on page 169. What? Where's this? I did this wrong. Let me do it this way. I don't want confusion something over here. So if you have this right here, let me do this again. I want to make it just crystal clear. That's true. Do y'all follow me in this? A and B are relative distances in a coordinate system. In this case, measured from the origin. If you look at this, when we have VB minus VA, it's equal to minus Q over 4 pi epsilon naught. And then we integrate dr, and we get minus 1 over r. Here, and it's evaluated from A to B. Now, when we do this, there's no constraint on where A and B are. I'm trying not to cause you any problem. The two negative signs cancel. So for this one, it's equal to Q over 4 pi epsilon naught, and it would be 1 over B minus 1 over A. Now, do you see that in his book? Class? What equation is it? Okay. And what I should say is, for this one, depends on which one is greater. If B is greater than A, this would be negative, assuming the charge is positive. And if A is greater than B, then it's positive. Do y'all follow me in this class? In my case, I had B less than A. Do you remember that up there? And therefore, this would be a positive voltage. Now, I want to make one point now, and I'm really trying to emphasize this. Whenever you have a positive charge, plus Q, the closer you get to this charge, the greater the potential is, positive potential. Do you all follow me? And by the same token, if it was negative, the closer you would get if it was negative, the more negative the voltage potential would be relative to any reference that you use. But here's what we do most of the time when we have a differential amount of charge. And this is important. Usually, what they'll say is this, and this is real important that you follow. I'm trying to get this all in this lecture. When you have a differential amount of charge that we can use as a building block, when we have dq here, and you have a distance, say, r from this, that's finite, and then you go to infinity, you're going to have r goes to infinity. I should say capital R goes to infinity. We're going to assume the voltage here, V in infinity, is 0. Now that's done all the time, and you can always do this assumption. You know, if there's no other constraints in the problem, you can always make the voltage at infinity 0 if it is a finite amount of charge. This is real important. So this is dq. And now I can say the voltage from here, we could do the E-field integration, but I can say the voltage here, point R, with respect to infinity being 0, is just dq over 4 pi epsilon naught and divided by magnitude of R. Now, box that. And this assumes V, as R goes to infinity, is 0. And that's very common. Now, the only thing I'm doing is let A go into infinity here. If A goes to infinity, you can see this term is going to go to 0. Y'all see that? The voltage at infinity would be 0 because 1 over infinity is 0. Now this is real valuable. Here's why. You see, this is a scalar. With me? One thing about scalars, the vector integrations are usually a lot easier than vector integrations of the electric field or anything when you especially have 3 components. You with me on this? So now I'm going to show you how valuable this is in calculating an electric field using this. Here's the next part of the voltage. Most of the stuff I just showed you, you've had before, right? In physics. Or at least you've been exposed to it. There's nothing here that's really unusual. And voltage is something, I think the first time you really did a lot of problems with voltage, I could be wrong, is probably in your circuits course. Where I don't know how did Dave Irwin explain voltage to you?
Potential difference.
Okay, I call it electrical pressure. Because that's literally what it is. If you have hydraulics or any kind of fluid mechanics courses, it's a direct analog to a pressure difference between 2 points. The flowing water is like current. You might say the cross-sectional area of the pipe is proportional to resistance. You can take a fluids problem, this is a nice thing, and you can turn it into a circuits problem, and it's a trivial thing. It really is. And it's easier to imagine stuff in fluid dynamics and stuff like this because that's something you get a handle on, you can see it. Right, now we're going to talk about why this is so valuable. So, if you take a look at the classic problem I did, suppose this is X, this is Y, this is in the book too, and this is Z, and I have a plate of charge, all right? It's simply a circular surface with a charge density. And say this has a radius A, and the charge density is rho s. Let's call it a constant charge density for starters. Now, if I want the electric field on the z-axis, we know we've done this problem, right? We found the electric field first from a loop, then we made a differential electric field from a thick loop, you might say, and then we integrated that value over the range of rho from 0 to A. You all remember that? Quite a few steps. Here, what we're going to do is this. Be attentive. What I'm going to say is I have a differential amount of charge right here. All right? And this is going to be my dq. Now, dq is going to be the charge density. I'm making it constant, but it doesn't matter if it isn't. And it's going to be times the differential surface. What is the differential surface on in circular or in cylindrical symmetry in the xy plane? Do you remember? D rho would be the radial distance, and then rho d phi would be the azimuthal distance. Do you all remember that? So you can say this is rho s times d rho times rho d phi. And now, based on that, I can say if I'm at a height z, say, yeah, that's the z-axis, but I'm just going to say this point, I want the electric field, and it's at a height z away, right here. With me? Well, now I draw a line from there to there, and I get this radial distance. We'll call it r. And that radial distance would be equal to the square root of z squared plus, and this would be this would be really the value of rho here, or it would be the radial distance measured from the axis to the point of observation would be rho squared. Do you all agree that that would be the radial distance, class? Remember, what I'm about to do is scalar. We're going to calculate the voltage. Might as well give you a heads up on this. If you want the electric field, you have the voltage in terms of coordinates like x, y, z. In other words, a functional form of voltage, not an actual value like 10 volts. Then you can take minus the gradient of the voltage to get the electric field. That's what we're about to do. If you look in the back cover of the book, I'm putting a few things together and try to make it on time. So if you look at the back of your book, right under that divergence, you're going to see gradient. You all see it? Gradient is a vector term. You're going to like it. It makes life easy. So, back to this thing. Now I get the differential differential voltage. So now I'm going to get the differential voltage there. Just watch me on this one. It's in your book, and that's dq, which is rho s times, really it's rho times rho d phi. Now that's the differential amount of charge. Then I have to divide it by 4 pi epsilon naught r. Remember, with differential voltage, it's a function of 1 over r. So it's divided by the square root of z squared plus rho squared. Right? Now that's the differential voltage. You all follow me on this, class? How many understand how I formulate it? The far back, you guys okay with that? Or not? You got it? I'm just taking a differential charge is the key, divided by 4 pi epsilon and r. Well, r is the square root of rho squared plus z squared. You all with me? Yeah.
All right.
put a rho in front of the D5.
Actually, you know what this is? This is D rho. This, my bad, this should be simply D rho. I'm very sorry about that. It should be D rho times rho d phi. I'm sorry. I'm thinking ahead on this one. I'm trying to fit it in. I'll get it in. All right. You okay with this, class? If you do this, if you have this as the differential voltage right here, then I need to integrate this, right? And I integrate with respect to rho from 0 to A, and with respect to phi from 0 to 2 pi. And that would give me the voltage at a height z, assuming the voltage at infinity is 0. This is the progression. This is in his book, but I don't remember the page number. If you're looking in the
It's
book,
173.
173? Oh, 173. Now, just look at this. This is V of z right here. The 4 pi epsilon naught is a constant. I take that out in front. I made rho s a constant. I'll take that out in front. It doesn't have to be a constant. If it's a function of only rho, you can leave it in there. You all follow me? Because it would be cylindrically symmetric. But I'm making rho s a constant. So I take it out. Now, when I do the integral of d phi, you see there's nothing that's a function of phi in it. There's no sine phi, no cosine phi. You all with me, class? When I integrate that, I just get phi evaluated from 0 to 2 pi is 2 pi. That's all. With me? Then, when I have the rest, now I'm left with the integral, and I'll put it down here so you can see it. The integral of rho d rho over rho squared plus z squared to the 1/2 power. And this would go from rho equals 0 to rho equal A. And I'm just stating the obvious, but I want to do it for a reason. With me? Now, if you're going to solve this integral, you're going to use a substitution, and this is the classic substitution. I'll just use u squared is equal to rho squared plus z squared, and then 2u, right? du is equal to 2 rho d rho, or simply u du is rho d rho. Do y'all agree with that? With me on this? Okay. Now, I'll do the substitution over here. First, the 2 pi and 4 pi give me 1/2. So I have rho s over 2 epsilon naught. And then I have the integral here. Rho d rho is u du. This is a really nice one too. And then I have, this becomes u squared to the 1/2 power is u. And I evaluate from u, from rho equals 0, which makes u simply z. And from rho equal a makes the upper part square root of a squared plus z squared. Take a look at that. Do you all agree with that? I'm just replacing the values. Now, what do you notice about the kernel of integration right here? What is u over u? 1. Do you all see that, class? It's just 1. People often say, I must have made a mistake. You didn't. It's 1. Integrate du, you get u. So I'll put that over here. There's a lot of classic problems with this. I want to do this one. This is in the book too. So here I can see that v as a function of z is just equal to rho s over 2 epsilon naught. And then I have u. So I evaluate. So it's square root, or really a squared plus z squared to the 1/2 power. And it's going to be minus z. And that's the voltage as a function of z. You'll notice the integration was trivial. It was almost boring. I mean, there's nothing tricky about it. The only thing you're doing is a substitution, and you got it. Y'all with me? Now, to get the E field, you have to go ahead and say the E field. Now, you'll notice this is a function of both A and Z, all right? A is a fixed variable, so derivatives with respect to a fixed variable. If I take a derivative of that with respect to rho, it's 0. Do y'all follow me? Z can vary at any height. Y'all with me? It can be any point we can observe the field. You good with this, class? So to get the E field here, we're going to say it's minus the gradient of V. This is only going to have a functional form of importance. It's a function of Z. So we say that's the derivative of V of Z with respect to Z in the AZ direction. Everybody with me on this, class? So go ahead and do that. Well, the rho over 2 epsilon naught, rho s, pardon me, over 2 epsilon naught comes out front. Then I take a derivative of this with respect to, remember there's a minus sign too. I didn't put it, but there's a minus sign, right? Now I take a derivative of that with respect to Z. Well, the first one becomes 1/2, right? Then it's going to be 1/2, and it's going to be a squared plus z squared to the minus 1/2, or it's 1 over square root of a squared plus z squared. And then I take a derivative of 2z right here, of z squared, which is 2z. And it's that minus 1, because the derivative of z with respect to z is 1. Do y'all agree with this, class? Everybody say this? Can you see it back there? Or not? Can you see? All right, the 2's cancel. This minus sign simply reverses the order, and you get really rho s over 2 epsilon naught here, and that's going to be 1 minus z over square root of a squared plus v squared. Now I've got a point to make. So that's the electric field. Do you remember calculating that? It's in the AZ direction, by the way. Do you remember us going through that, calculating by a differential, from a differential fat loop? You got the electric field in Z direction, and we integrated it over where the loop existed from 0 to A. It's a lot of work. Here, it's straightforward. One thing I want you to know here, and this is a sanity check. You know, if this loop went with a radius of infinity, it would look like an infinite plane. Do you agree with that? Well, what happens to this value as A goes to infinity? This term goes to 0, doesn't it, class? And therefore, it's just rho s over 2 epsilon naught. Do you all remember that being the electric field from a line or from a plane of charge? It checks that box. It's a sanity check. I wanted to get through that today, and I want to tell you one other thing. Now, I'm going to give you problems about voltage. Some of these you're going to feel a little clumsy doing. But remember, if you are asked for the electric field for a lot of these crazy distributions, it's much easier, in my opinion, to calculate the voltage and then take minus the gradient. As a matter of fact, for most numerical methods that we do, computer simulations of the real world, we'll solve potentials. In other words, the potential is the voltage. We'll take the we'll take the gradient of that numerically to get the electric field. It's much, much easier. All right. Do I have another minute? I do. Are there any questions? I don't think I have time for another problem, but can you all see that this stuff kind of lends itself to simplicity? Because if you can get the differential voltage from any charge distribution, it's pretty easy to find the total voltage by simple limit. Pretty easy in general. Okay? All right, have a great weekend. Anybody going down to the game? Yeah. Oh, gosh. Yes, sorry. I wish you would have reminded me earlier. Class, I told everybody that I'd let you schedule the midterm. Do you have a date for them? Let's just do that.
October 6th.
Hold on.
6
Say it again.
October 6th.
What day is it?
That's Friday.
Or October 6th,
or
October 9th.
October 9th. The lunch is Monday.
Okay, just wait, no, why was that?
The 9th.
All right.
The 9th.
Any other dates?
No.
All right, want to make one comment, This is just based on my observations over 38 years of teaching. Most of the time, Monday exams have higher averages.
Okay.